Hello there, welcome back to the new video. So today we'll be talking about this very interesting paper, which is titled as Task-Aware Representation of Sentences for Generic Text Classification. This is from researchers from Zalando SC and Humboldt University. So at very high level, this paper essentially introduces the drawbacks that we have in current day's state-of-the-art text classification system, which majorly follow pre-trained fine-tuned paradigm, and talks about how we can use these existing systems and use them to perform zero-shot or few-shot learning. So yeah, let's start with the abstract. But before that, if you're new to this channel, make sure to hit that like button and subscribe to the channel. Also share it across with your friends to whosoever is interested in this content. Also have a free email subscription service where I'll be sending you an email per month regarding all the videos that have been released on this channel for the past month. And you can find the link for that in the description box. Make sure to sign up. Cool. So as they write, state-of-the-art approaches for text classification leverage a transformers architecture with a linear layer on top that outputs a class distribution for a given prediction problem. So yeah, that's how current day systems work. Let's say we are trying to solve a task of sentiment analysis where you have, let's say, positive and negative. These are the two labels that we have. Let's call them as O1 and O2. The first thing that you do is to pick a pre-trained language model. Let's call it as BERT in this case. You pre-train this BERT model on masked language modeling and next sentence prediction task by feeding in large amounts of domain corpus that you have, which in our case would be all the reviews. Okay, so yeah, what I just mentioned is to pre-train with the domain corpus is second level of pre-training that I was talking about. So the BERT model that you pick from Google, right, is already pre-trained on Common Crawl, Wikipedia, all of that corpus. So one way is to use that and directly fine-tune through supervised signals. Other is you use that model, pre-train it again with the domain corpus that you have, which is a second level of pre-training, and then you can again fine-tune it on supervised data. So yeah, these are the two typical ways to how people usually do. Now the problem that you can see over here, right? BERT is an encoder, and usually we have a linear layer that we put on top of the representations that you learn from BERT that derives as a distribution across the output classes, which in our case would be just 2, so we can easily use a sigmoid layer. Now this linear layer, the weights that it learns is very much task specific. And for this entire system to now work for, let's say, topic identification, will require us to discard the previous learning and relearn the weights for this linear layer. And apart from this, you might also want to pre-train BERT again for that topic identification dataset. So if you can see, right, there's a lot of relearning or unlearning that's happening if you want to scale this system and directly apply onto different tasks. So clearly this is a computational challenge. Apart from this, you might be limited in the terms of data that you have for the newer tasks. So for, let's say, as I said, right, we have a sentiment model ready. We want to apply it to topic identification. And let's say there were 4 topics that we had, but we don't have enough data for that, which means the weights that you're going to learn won't be sufficient and be fitting to the underlying task. So then how do you deal with such low resource situation is again one more question. So this paper tries to answer all these questions by introducing a new learning way by formatting a data little differently. So we'll see to that as we proceed forward. In the meantime, they have also mentioned the limitations that we have with current state-of-the-art text classification systems, which is that the number of classes to predict needs to be predefined, which is true because in sentiment classification, you should be knowing like you are training your entire model for 2 classes. Now in transfer learning setting, if a new class is added to the already trained classifier, then you'll have to discard all the information that's already there in the previous linear layer learned, which again is what we saw in the case of sentiment to topic transition. Then the second disadvantage is that these systems learn a semantic meaning of these classes implicitly through the training samples. So which means they are not essentially understanding the word, let's say, positive or sports for that matter. They are deriving the meaning of these words based on the training sample that they see. But it might be really helpful if you already know what this class label actually means. Because in that case, now if you add a new class label, and if that's similar to what you already had previously trained on, then even if you have less data for this newer class, you can perform some sort of classification based on the similarity of the label. So this is what they call as leveraging the explicit semantic information that is there in the natural language names of the classes. So yeah, these are the 2 limitations that the authors discuss in this paper and try to come up with the solution of that by presenting a novel formulation of a text classification that addresses these limitations. And on evaluation, They found the system to be significantly outperforming previous approaches when your training data is small or if you're trying to learn a new class with no training data at all. Cool. So let's move forward and see the approach that the authors propose. So they formulate every text classification task as a universal binary classification problem. So if you see this equation, this is how a typical text classification would work. You want to learn a function f that takes in an input text and then maps it to a one-hot encoded vector of m dimensions, where m is nothing but the number of classes that you have in the output. So that's what the probability you want to learn. Now in the case of multi-class classification, you would have one output, so that will have a softmax over this entire size m. Whereas under the multi-label classification settings, since multiple labels can be true, you can have multiple ones in that hot vector. Now clearly this is infeasible if you want to reuse the same function for a newer task that might have more number of labels. So clearly then this retraining will have to be done again to incorporate that m+1 cell as well. And for that to happen, you need to have data that corresponds to that newer cell. So all of these things are kind of limitations, to which they propose a generic binary text classification task, where again still you want to learn a function f, which now doesn't take just the text as an input, but also the task label, which is the output class, and then just says if it's 0 or 1, which intuitively it's trying to just match or learn relationship between the task label and text and say whether this belongs to this or not. So this is how it would look. You have the true label yi, you have the actual text t, and you want to say whether this is true or not. And you do this for all the unique m labels that you have. So clearly by now you have noticed that the size of data is going to increase, right? Because what was happening earlier was you have, let's say, this as a sentence, you train it against a vector of outputs where one would be, let's say, 1 in case of multi-class. And in this way, the total number of samples in the dataset that you have that will be used for training purposes is nothing but the number of sentences that you have. Whereas in this case, since you are also appending task label and the output is just true or false, you'll have now a lot more input samples to train your model with, because it could be, let's say, sentence S, and if it's a sentiment classification, you would say positive sentiment and the answer would be 1. For the same sentence, you can have negative sentiment as the label and the answer would be 0. So clearly the data is being multiplied by the number of unique labels that you have. Okay. So yeah, again for, let's say, topic classification, this was the actual sentence. You would append the topic also, which is politics, with this keyword, and then pass it through a BERT and then a linear layer, which is a decoder, and have an output of 0 or 1. Now in this case, if you can recall, right, the task of decoder is to map that dense vector in a 0 and 1 classification setting. So now this has become kind of generic and can be used across classes. Unlike the previous versions, where the job of decoder was to map it to m number of classes, which could differ from task to task. Here, since we are putting our m as fixed, and it will be same across all the classes in terms of its semantics, this is generalizable across multiple tasks. So if you see this figure, so let's say we have 3 tasks, which is sentiment classification, topic classification, and question type classification, where you have label and text for each of them. You create such pair, format them in the BERT way, where you start off with CLS token, followed by tokens for the label, separator token, then tokens for all the text that you have, and then finally ending with the separator token. Pass it through the BERT model. At the output, you'll get the representation for every token, but you utilize the classification token representation, pass it through a linear layer, and do a classification of whether it's true and false. Now clearly, even if the tasks were different, the same architecture can be reused for each of these tasks. And once you now train with all these 3 tasks, you have just one architecture, to which now if you input, let's say, another topic and its text, the architecture should be able to give you whether it's 0 or 1. And with such a formatting, intuitively what's happening is you are also using the explicit meaning of the label while making a representation for any of the tokens. And vice versa, you're also learning an implicit representation of the label by making use of the representation of the tokens from the input sentence, which in a co-attentive setting is helping us to learn a representation that tries to learn a relationship between the label and the actual text. Okay, moving forward. So here they explain the same thing. Okay, talking about training and prediction, as you have already seen, you have now a tuple as an input mapped against a true and false label. And you train the entire system in a typical cross entropy loss, where you fine tune the parameters of your linear layer as well as the BERT model. So in this equation, as you can see, right, X is common, which is this text. Let's say I enjoyed the movie a lot. Whereas the Y label is going to change because the number of unique labels that you have will determine the number of samples that you want to generate for a single unique X. Which in our case, let's say if it's 2, M is equal to 2, then you'll have 2 samples per X. Okay. So they say that the core advantage of their method is the entire model because of the generic target. And then depending on the task that we are trying to train on, if that's really similar to the existing task, then even the zero-shot scenarios can be enabled. So we'll see to all those results in the experiment section. And as we have already discussed, since we are now extrapolating an example into m number of examples, so accordingly the number of forward pass that you do per unique sample X would also increase. Because earlier for every task, you were doing one forward pass to get a distribution across all the labels. Whereas now, since you have paired those labels with the input samples, you'll have to do m forward pass to cover one unique input sample. So that way the computation is going to increase. But the good thing is that the model parameters that you're going to learn will all be shared and can be used across all the tasks. Whereas with typical text classification setting, you would train multiple models, each fitting its unique task. So talking about the experiments, they try to address 3 major questions. Is that how well the model is able to transfer to new classification tasks with little training data. So that's the first question, when semantically the source and the target tasks are pretty different. And then finally testing the capability of the model under the situation where you don't have any data for that particular task. Okay. So they tested on 3 task types. One was the question type classification, where they used Trek 6 and Trek 50 datasets, where the source had 6 classes and the target had 50 classes. Then the second task was topic classification, where they used DBpedia and AG News, where DBpedia has 14 classes and AG News has 4 classes. And finally the sentiment analysis from Yelp to Amazon, where both of them had 5 classes each. So this M over here, what you see is nothing but the number of classes in the target corpus. K is the number of samples they use from target task per label. BERT base is a standard non-linear transfer learning variant in which you just fine-tune a pre-trained BERT model on the target task. Whereas BERT base FT, what you see, is a traditional transfer learning variant where you first train on the source corpus, in this case the Yelp full, and then fine-tune it on Amazon full. And TARS is the method that they propose. So for the first row, where the value of K is equal to 0, which means you don't have any sample for the labels present in the Amazon full dataset, the method was able to scale pretty well and give them a score of 51.8. Whereas now if you have, let's say, 2 samples per label, a typical non-transfer learning would give you 24.6 score. Whereas if you fine tune with those K samples per label, after training on Yelp full, you'll be getting 36 score. And with TARS, you were getting way higher score, which was 52.7. So clearly the model is able to scale really well under the few short learning capabilities. And as you increase the value of K from 0 to 100, now both the BERT base and BERT base fine tune become better, and which is again pretty much close to what their system also gives. So which kind of hints like if you already have a lot of data available for the target task, then probably you might want to go in a typical way of first pre-training and then fine-tuning, which is BERT base FT. So similarly, if you see topic classification, DBpedia had 14 classes, AG News had just 4 classes, so which means the number of classes are also now differing. So with number of only 2 samples per class, you get a score of 74.3 on the target dataset. So yeah, that again affirms its productivity in case of few short learning. And similar with question classification. Also in this figure, they evaluate the zero-shot capability of the model for topic classification, where the model sizes were almost same, and the base model to which they compared was the GPT-2 model. So under no example at all for the target dataset, they were able to get scores higher than what GPT-2 would have given them. So yeah, that again is a pretty cool result. Okay. They further did an experiment to check cross-domain transfer. So the earlier table, what you saw, right? The task was still same. Let's say for sentiment, you use D1 and D2, where the number of labels could differ, where the source had 14 classes and the target had just 4 classes. So which means keeping the task same and changing the dataset along with the number of classes, the TARS model what the authors have proposed was able to perform really well. So here we see what happens if you train it on, let's say, topic classification and test it on question type detection. Or for example, if you train it on sentiment classification and test it on topic classification. So DBpedia topic had 14 classes, Trek had 6 classes, Amazon Full had 5 classes, and AG News topic had 4 classes. So here we are also defining the task as well as the target labels. So here again we can see like their model is able to perform really well and is able to beat transfer learning way as well as the non-transfer learning way of learning the target distribution. Whereas things are pretty different if we see from sentiment to topic, the BERT base overpowers the remaining results. And that too with a pretty good margin under the few short scenarios. Also, since the tasks are pretty different, the BERT base, which is a dedicated model and doesn't use any transfer learning approach, performs pretty well than if you would have first trained on sentiment and then fine-tuned on topic. So again, clearly seeing these two tables hints like the choice of your source and target task clearly defines which method is going to work well. But in general, as we saw in the previous table, scaling across same task but with different datasets, TARS was able to outperform other two methods for all these three datasets. So yeah, okay. So yeah, I think we are done with the paper now. So if you like such content, make sure to hit that like button and subscribe to the channel. Also share it across with your friends to whosoever is interested in such content. I'll meet you in the next one. Bye bye and take care.